Welcome to this explainer. Today, we're cracking open one of the most fascinating black boxes in modern AI, the routing mechanisms inside mixture of experts architectures. Now, if you've been following the rapid scaling of large language models, you already know that MoE is the underlying engine driving massive capacity without totally bankrupting your compute budget. But understanding this is absolutely crucial because routing inefficiencies, they directly translate to massive real-world costs when you're running these models at scale. So how does that router actually decide where to send the information? Well, a pretty groundbreaking new arXiv paper titled "Is MoE Routing a Huffman Code?" reveals a hidden, almost elegant mathematical truth behind these choices. Let's dive in and break it all down.
Listen to this bold claim straight from the researchers. MoE routing is not merely selection, but a manifestation of Huffman coding. What they're proposing here is honestly revolutionary. They're suggesting that optimized AI models aren't just out there randomly picking experts. No, they're spontaneously acting as information theoretic engines. They are instinctively learning to compress information based on the fundamental laws of data communication.
All right, let's get into Section 1, inside the MoE black box and the discovery.
To really grasp what the paper is claiming, we kind of have to rewind back to 1952 and look at the concept of Huffman coding. Think of it like a giant puzzle, or better yet, just think about how a zip file works on your computer, or even Morse code. To be efficient, you assign short, simple codes to the stuff you encounter all the time, the high-frequency information. And conversely, you save the longer, much more complex codes for the rare, unusual information. The researchers hypothesized that a smart AI router should do the exact same thing. It should assign shorter, simpler routing paths to common semantic tasks and reserve the complex expert combinations for the rare ones.
Which brings us to the formal introduction of the paper's massive breakthrough, the frequency diversity law. This law basically states that optimized MoE models naturally evolve to follow those exact Huffman principles. Driven purely by the desire to minimize prediction loss during training, these models automatically start allocating fewer unique experts, which is essentially a shorter code, for common everyday logic. But when they hit a rare, highly complex task, they invoke a really diverse combination of experts, giving it a longer code. And the proof here is just undeniable. The researchers tested this law on state-of-the-art models like Gemma 4, 27B, and 5, 3.5 MoE, and the results? A mathematically perfect Spearman correlation of 1.00. I mean, the models followed the law flawlessly. This brilliantly illustrates a phenomenon called temporal compression during chain-of-thought reasoning. When these models start a complex reasoning trace, they're a bit uncertain, right? So they activate a broad, diverse set of experts to explore the problem space. But as they progress and start figuring out the solution, they compress their routing. They start relying on a very small, compact core of high-frequency experts. They're literally adapting their code length to the evolving complexity of a problem in real time.
Moving on to Section 2, uncovering the redundancy trap. Because, well, it's not all smooth sailing. So, the Huffman setup sounds like a flawless system, right? Well, brace yourself for a pretty massive plot twist. Does aggressive load balancing actually ruin routing efficiency? You see, during training, engineers use load balancing to basically force the AI to use all of its experts equally, just so none of them go to waste. But when the researchers investigated the Qwen 3.535B model, they found a glaring anomaly. Instead of that elegant Huffman efficiency we just talked about, Qwen showed a completely reversed anti-Huffman routing trajectory. Let's take a look at why.
Get a load of this statistic from the paper. 0.886. That's 88.6%. That number represents the minimum average pairwise cosine similarity between Qwen's experts. What does that mean in plain English? It means the vast majority of the model's experts are functionally identical to one another. They're virtually indistinguishable clones.
Let's break down this Qwen anomaly a bit more. Qwen has a massive pool of 256 experts, and it uses extreme routing sparsity. It activates only about 3.1% of them at any given time. Because it was heavily forced to load balance across such a huge pool, the model essentially, well, it cheated. It creates highly redundant clones of experts just to satisfy that balancing objective. And because of this, the router wastes incredible amounts of effort simply picking which identical clone to use, rather than encoding actual semantic logic. The underlying beautiful Huffman efficiency, it's actually still there, but it is completely masked by this massive web of functional redundancy.
Which brings us to Section 3, Subset Difference Pruning. Let's see how they fix this.
So, how in the world do we rescue a model from this trap without spending millions of dollars to retrain the whole thing? Subset difference pruning builds a solution step by step, and the best part? It's entirely training-free.
First, the algorithm computes how similar all the experts are based on their activation profiles. Second, it systematically finds the pairs that are essentially duplicates of one another. And third, this is the crucial step, it surgically masks out the clone that is used slightly less often. It literally just sets its routing probability to negative infinity, meaning the router is simply no longer allowed to use that redundant path. The results of doing this pruning are absolutely fascinating. The baseline Quen models started with a negative anti-Huffman correlation of -0.631. But watch what happens when they surgically mask out just 10% of those redundant experts. The model flawlessly flips back to Huffman compliance with a positive 0.567 correlation. And the accuracy, on the GSM-8K math benchmark, it barely drops. It goes from 93.6% down to just 91.9%. Now, obviously, if they push it to 20% pruning, the correlation stays positive, but the accuracy drops pretty significantly. So there is clearly a sweet spot for removing just the right amount of redundancy. Now, you might be wondering, were those pruned experts just dead weight anyway? The activation data completely proves otherwise. The pruned experts actually handled nearly a quarter of all the model's activations. They were highly active, but because they were functional clones, when they were removed, the router seamlessly adapted. It effortlessly shifted that heavy traffic to the surviving identical experts in the retained pool, instantly streamlining its logic paths.
All right, final section, section 4, routing is semantic compression.
This all leads us to an incredibly practical takeaway, Huffman compliance as a health diagnostic. Because this relationship exists, researchers no longer have to just guess if their model is falling into a redundancy trap during an expensive training run. They can simply calculate the Huffman correlation, the R value, as a lightweight task-free probe. If that correlation turns negative during training, they immediately know, okay, our load balancing is generating functional duplicates way faster than it's creating meaningful expert specialization. So this leaves us with a pretty massive question to consider. If we now know for sure that AI routing is fundamentally about compression, about achieving the minimum description length, should this become the ultimate blueprint for all future AI architectures? Perhaps the next generation of large language models shouldn't be forced into arbitrary load balancing at all. Maybe they should be explicitly designed from the ground up to operate as principled compression engines. It's a complete paradigm shift, and it could completely redefine how we scale intelligence. Thanks for joining me on this explainer today, and keep questioning the black box.